Hi! In this video, I'll provide a brief overview of our method and show some qualitative results across multiple datasets. Given an image, large-scale 2D segmentation models, such as Segment Anything SAM, can generate high-quality zero-shot image segmentation at multiple levels of granularity. However, when we try to deal with multi-view images of a scene, the outputs from SAM are usually not view-consistent. As you can see, some segmentation masks are missed in other views, and there are some contradictions between views. In this paper, we propose a method that can generate view-consistent hierarchical segmentation with a view-inconsistent multi-granularity segmentation masks from 2D segmentation models. In our method, we train a nerf with an ultrametric feature field using images and view-inconsistent segmentation masks from SAM. During the training phase, we use the pose images and the segmentation masks in each view to train a nerf with feature field with ultrametric contrastive learning. After training, we use the estimated depth in the rendered feature maps to construct a 3D point cloud of the scene, with ultrametric features assigned to each point. Given a threshold T that indicates the segmentation granularity level, we then use a traditional segmentation method called watershed transform to segment the point cloud in 3D. This will give us 3D consistent hierarchical segmentation results. The key idea in this paper is to learn an ultrametric feature space. Unlike a Euclidean space, it shows transitivity in distance-based grouping, which naturally leads to hierarchical clustering. In this slide, we'll explain how an ultrametric distance is defined. The ultrametric distance is based on a graph. It represents the shortest path between 2 points, but the length of that path is determined by the longest edge along it. Let's look at an example. On the left, we've overlaid a simple graph on the image, where the edge lengths represent the feature distances between points. We then calculate the ultrametric distances between those points and organize them into a hierarchical tree, which you can see on the right. The numbers on the tree represent the ultrametric distances between nodes on the 2 branches. This demonstrates how the ultrametric space can naturally lead to a hierarchical structure of the graph. After organizing the scene into a hierarchical tree, we can easily use different distance thresholds to segment the scene at various levels of granularity. We evaluate the method with 3 metrics on the Blender dataset. The result shows that our method produces not only more accurate, but also view-consistent segmentation results. On the PartNet dataset, our method outperforms other baselines in evaluation based on multi-view segmentation maps. Besides, our method can achieve comparable NC score on the finest level as a supervised point cloud segmentation model, 3D-PIS. These are the qualitative results on the Blender dataset. You can see that our model can segment the scene at different levels of granularity and generate these view-consistent hierarchical results. Similarly, our method can segment the Lego scene hierarchically. You can see that our method can even segment out some small Lego bricks in the scene at the finest granularity level. This is a video that shows our results for a real-world scene from the tanks and temples dataset. We can see that our hierarchical segmentations are view-consistent as it's based on the 3D point cloud. This is a result from another real-world scene in the LLFF dataset. Our method can segment the scene hierarchically and remain view-consistent. You can find more qualitative results in the paper and the supplementary materials.